Hello everyone, welcome back to Introduction to Semiconductor Devices. In the last lecture, we looked at the basic biasing schemes for the PN junctions. So essentially we have forward bias and reverse bias, and we looked at how the band diagrams will change for these conditions. And then we looked at the injection of excess minority carriers. So quickly to recap, we have seen that if you have reverse bias, diffusion is insignificant. Diffusion is, you can say, even absent because there is a large potential barrier. Diffusion is absent. Okay. So, and there's also small contribution of drift because there's an electric field. There's going to be a drift of minority carriers, and since the total number of minority carriers is small, the drift current is going to be small. Okay. This is for reverse bias. When you come to forward bias, we saw that the potential barrier is reduced, and because of which you have the drift of drift of electrons from N type to P type and holes from P type to N type, right? So forward bias implies diffusion is dominant, is significant, whatever. There is going to be a small contribution of drift, but that is going to be negligible when compared to the diffusion contribution. And then we also looked at how the excess minority carriers are injected. We saw this, that at the edge of the depletion region, we can write an expression for the holes. In this case, holes are getting injected from the P-type semiconductor. So the Pn, the holes injected into N-type at x equal to Xn is going to be the equilibrium hole concentration times exponential QVA by KT. Okay. So I need you to really, go through it multiple times. That's the reason why I'm also writing it, so that you will sort of understand the full thought flow. Okay. And what about the electron concentrations in the P type at x equal to minus xp? This is going to be the equilibrium electron density times exponential QVA by KT. So this is at the edge of the depletion. And once you have that, we can solve the minority carrier diffusion equation and we can get this exponentially decaying profile. Why do the holes decay as you go deeper into the N-type semiconductor? The reason they decay is that they will recombine with the electrons and then the holes are removed. So essentially we go back to equilibrium. Right? This we have discussed in the lecture about excess minority carriers. Okay. And similarly, you have for electron, there's a decaying profile in the P-type semiconductor. So today, we would like to determine the current in the forward direction. In this video, we will talk about current in the forward bias regime. So, well, you have electron diffusion and hole diffusion. What is the direction of current? If you analyze, if you look at just the electrons, I just want to draw the gradient. So essentially, as a function of x, if I want to draw how the electron concentration is changing, I see that electrons are increasing as you go from left to right. Okay. And the current direction is essentially, because electrons are going from right to left, Jn diffusion is going to be from left to right. Right. So what's happening is you have, this is the Jn diffusion, and your gradient dn by dx also is in the same direction. Okay. Whereas if you look at holes, the concentration of holes is reducing as you go from left to right. Okay. And the current, hole current is essentially, this is, I don't know what, this is P. So this is Jp diffusion, right? The hole current is in the left to right direction. So Jp diffusion is left to right, whereas dp by dx is in the opposing direction. And that is why we can write basically the total current, J total, is going to be Jn diffusion plus Jp diffusion, right? The total contribution is from electrons and holes. The drift is not going to contribute significantly. So we can write this as Q dn diffusion, Q dn d delta n by dx minus Q dp d by dx of delta p. So this delta N and delta P are the excess minority carriers, right? And note, this is coming because this sign is coming due to this. The diffusion current is actually opposing the gradient. That's why there's a minus sign. Okay. So now we can easily derive the currents. Okay. Let's do it for holes. Okay. So first let us write out what is the excess hole density. We can write, I mean, this is a function of x. So this is going to be the total hole density, right? Which is going to be Pn naught into exponential QVA by KT minus 1. So, or rather, yeah, this is minus 1 I'm putting in. So essentially I'm taking, this is my excess Pn at x equal to xn, right? And we know that as you go deeper into the semiconductor, there's an exponential decay. So this guy should be multiplied by exponential minus x minus xn by LP, right? So this is essentially capturing the diffusion length. So what this is telling you is that as you go deeper into semiconductor, there's an exponential decay. Okay, so let's take the derivative of this. Okay, since the diffusion term has a derivative, let's do that. d by dx of delta Pn is going to be the whole term, right? Pn naught exponential QVA by KT minus 1 times exponential minus x minus xn by LP times the derivative of exponential. So that's going to be minus 1 by LP. Okay. So now JP diffusion is going to be minus Q dP d by dx of delta Pn. We don't need to compute this at all x. We just need to know it at x equal to xn. Because at other points it's going to reduce, but let us focus on that because that's where the maximum diffusion current is going to be there. Okay. So then this is going to be equal to the minus and minus will cancel out. So you get Q dP Pn naught by LP into exponential QVA by KT minus 1. Okay, this is the whole diffusion current. And similarly, you can write an expression for the electron diffusion current. So the total current, J total, is going to be Jn diffusion plus Jp diffusion. That is going to be, I will take QVA in common. So basically I can write Q dP Pn naught by LP plus Dn by symmetry. I'm just writing in the expressions ln into exponential QVA by KT minus 1. This is the total current. Okay. And this particular term here, the brackets, we call it reverse saturation current. We will see in a moment why that is. But anyway, this is the overall form. Okay. So now, so how does the current look like? Well, you could summarize it this way. The same expressions now is written in more legible form here. So that's a reverse saturation current. And your current is going to be exponential QVA by KT. So immediately you see that as the applied voltage is increased, as VA is increased, the exponential term will grow significantly, and then that will dominate. So in the forward direction, your PN junction tends to contribute. The current tends to increase exponentially as you increase voltage. Whereas if you go to reverse bias, what happens is as VA, okay, I can write if VA is greater than 0, J is basically exponential dependence on QVA by KT. If VA is less than 0, J is going to be equal to approximately, the exponential term is going to become 0. So 0 minus 1, so minus 1. So it's going to be approximately minus Js. Okay. So that's why the current can be drawn for a diode in this fashion. So for negative voltages, you have a constant current. And as you go into forward bias, it starts increasing exponentially. So this is the action of a diode, which we must have studied in our +2 and so on, right? So that's how you get these expressions. We can analyze these expressions a little bit. We can make a couple of points. The first one is, you see here that there is a NP0 and PN0. These are minority carrier densities. And we have seen that the minority carrier densities are essentially dependent on doping and Ni, right? So I can write my minority carrier density in this form. So I'll say Js, the saturation current, I can write it as QdN. For NP0, I'll write it as Ln in the N you want. So basically this is going to be Na, okay, plus Q dP Ni square divided by Lp Nd. Okay. So one of the important things we'll see here is the saturation Js, right? Saturation current density, it exhibits strong dependence on the temperature and band gap, right? Because we know that Ni is having a strong dependence on the band gap and temperature. So Js also exhibits strong dependence on Eg and temperature. For example, we have seen Ni was what? For silicon, it is 1.5 into 10 power 10, right? For silicon, for germanium, it was, I think it was 2 into 10 power 13 for germanium. Whereas for gallium arsenide, it was 2 into 10 power 6. Right. So you see that if you make a diode out of different materials, immediately you're going to have a dramatically different saturation current density. So saturation density, current densities cannot be compared across materials. See, because it's Ni square, the saturation current density has Ni square dependence. So the dark currents will be much, much higher in germanium, whereas in gallium arsenide, they're going to be small. Okay. So this is one of the points we can make from the expression, just purely mathematically. The other thing is, we have introduced what is called as a one-sided junction. So what happens in a one-sided junction? We said that if one of the doping densities is higher, for example, let's say Na is much, much higher than Nd. So what current will flow essentially? So essentially this is going to mean that since Na is higher, the contribution, this in the expression here, Js will become Q dP Ni square divided by Lp Nd exponential QVA by KT minus 1. The reason this happens is Ni is in the denominator for the electron term. So electron term is not going to be significant. Okay. So, it could also be understood physically. Na is high means the P region has large number of holes. And this large density of holes is getting injected into the other side. So the current is going to be predominantly in the form of hole diffusion. The electron diffusion contribution is going to be negligible. Okay, that's what this means. So depending on what type of doping is high, that is going to dominate. If you have a N-type doping higher, that Nd is higher, then electron diffusion is going to dominate. So we can look at relative doping densities and decide, what is the dominant contribution. So overall, we see that The current in a diode exhibits an exponential dependence. And I forgot to mention that, if you look at this exponential, you can draw basically an intercept where it intercepts the x-axis, draw the current and take it to intercept. And this point is called as Vt, and which we call as threshold voltage. So it's kind of a voltage at which essentially the diode turns on. Okay? You have a large current flowing. Below that, it doesn't allow any current to flow. So that's the diode action. And we will analyze a few more things, especially the reverse bias, reverse saturation current. We will analyze in a little bit more depth in the next video. So, but I would like to stop here and then we'll continue in the next video. Thank you.